A projection measurement is a type of quantum measurement that describes the process of projecting a quantum state onto an eigenstate of a particular observable. This type of measurement is also sometimes referred to as a projective measurement. When a quantum system is measured through a projection measurement, the possible outcomes correspond to the eigenvalues of the observable being measured. The probability of obtaining a particular outcome is given by the square of the projection of the state onto the corresponding eigenvector. The projection measurement can be used to extract information about the quantum state of a system, and it plays an important role in the interpretation of quantum mechanics. It is a fundamental concept in quantum physics, and it has numerous practical applications in fields such as quantum computing, quantum cryptography, and quantum sensing. Projective measurements are described by an observable A matrix and an index I that represents the possible outcomes in an experiment. The observable A is a self-adjoint operator on the state space of the system being observed. The observable A can be written in the form of spectral decomposition. In quantum mechanics, a system can exist in a superposition of multiple states until it is measured. When the system is measured, it collapses into one of the possible states with a certain probability. After projection measurement, the system is in a specific state corresponding to the eigenvalue of the observable being measured. This state can be described by a wave function that is no longer in a superposition of states. The wave function is said to be collapsed to a particular value, and the system is said to be in an eigenstate of the observable. The precise state of the system after projection measurement depends on the specific observable being measured and the initial state of the system. For example, if the observable is the spin of a particle, the system could collapse into an up spin state or a down spin state with a certain probability. If the observable is the position of a particle, the system could collapse into a specific position with a certain probability. In quantum mechanics, the average value of an observable is the expectation value of the observable in the system state. The expectation value is calculated by taking the inner product of the system state with the operator corresponding to the observable, and then taking the complex conjugate and multiplying by the state again. The result is then normalized by dividing by the inner product of the state with itself. After projection measurement, the system is in an eigenstate of the observable being measured. The eigenvalue corresponding to this eigenstate is the outcome of the measurement. The average value of the observable after projection measurement is simply the eigenvalue itself, since the system is now in the eigenstate corresponding to that eigenvalue. The variance of the observable after projection measurement is zero, since the system is in a definite state corresponding to a single eigenvalue. Variance is a measure of how spread out the values of an observable are in a given state. If the system is in a superposition of states, the variance will be non-zero since the values of the observable can differ depending on which state the system is in. However, after projection measurement, the system is in a single state corresponding to a single eigenvalue, so the variance is zero. Overall, after projection measurement, the average value of the observable is simply the eigenvalue corresponding to the eigenstate the system has collapsed into, and the variance of the observable is zero since the system is in a definite state. Quantum measurement is described by a set of measurement operators that act on the state space of the quantum system being measured. The index I represents the possible outcomes of the measurement in the experiment. If the quantum system is in the initial state ket psi before measurement, we can calculate the probability of each possible outcome. Measurement in quantum mechanics projects the quantum state ket psi onto another state ket alpha. The probability of obtaining this state is the square of the inner product between the two states. In some cases, the quantum state will be projected onto one of its orthogonal states with a certain probability. After the measurement, the quantum state collapses to the state that was measured. Since the sum of probabilities for all possible outcomes is 1, the measurement operators must satisfy the completeness equation, which states that the sum of the product of the transpose conjugate of each operator with itself equals the identity matrix.